Labguy here. Today, in part 3 of the Bob O scope, I'm going to do a deep dive into the function and operation of the X and Y deflection amplifier. This is the board I designed that takes a low voltage drive of 0 to 5 volts and increases it up to plus and minus 150 volts for driving the deflection plates of a cathode ray tube. And we will be applying this to the 3D/130 GH 1-inch CRT by Brimar, or more precisely a 5-centimeter tube. And we'll take it from there. So without further ado, let's get into the deep dive, shall we? Today's video will examine the deflection amplifier I designed to use with electrostatic cathode ray tubes. Let's start with the schematic of the entire XYZ amplifier board version 2.0. It consists of 2 differential deflection amplifiers and 1 experimental video amplifier. The video amplifier does not work as designed and is not being used in the current configuration. So we will not be covering that part in this episode. Instead, let's look at the X and Y amplifiers. Both channels are identical in operation, so we need only study one channel. This amplifier consists of a constant current source and a classic differential amplifier, also known as a long tail pair. This circuit has 2 inputs and 2 outputs. It can be driven by 2 inputs, or it can be driven by 1 input with the other input held at a constant DC level. This latter method is the one we will be using in this project. The inputs are the base input pins of transistors Q1 and Q3. These are buffered through variable resistor RV1 and RV2. In normal operation, a signal between 0 volts and plus 5 volts is applied to the top of RV1. This pot is used to set the output voltage level. RV2 in this case would have a steady plus 5 volts applied to the top of it. RV2 operates as a DC balance control to make the collector output's nominal DC voltage equal after the correct operating level is established by RV1. By correct operating level, we mean that the scan on our CRT is set to the desired width or height. This circuit's magic begins in the constant current source consisting of U1 and Q2. U1, a TL431, is a precision voltage reference generator that is more accurate over temperature than a Zener diode, though a Zener diode could be used at this point. In the simplest form, a 2-resistor divider is used in place of the Zener diode. You can do that if you are trying to build a temperature sensor. If the reference voltage changes, the size of the CRT scan changes, smaller when cold and larger when warm. The NBTV cathode ray televisor suffers from this defect and will be upgraded to this design in the future. To alleviate and avoid temperature issues, I chose to use a precision voltage reference originally manufactured by Texas Instruments, the TL431. Specifically, the TL431LP in the TO92 package. The same 3-lead plastic package as the transistors on this board. The TL431 is fully compensated and will provide a constant voltage regardless of temperature. The TL431 can be programmed for any voltage between 2.5 and 36 volts with 2 external resistors, but let's keep it simple and simply connect the VREF pin to the cathode pin of the device. VREF is shorthand for voltage reference. This configuration produces the equivalent of a 2.5 volt Zener diode. In this circuit, the TL431 cathode is connected to minus 12 volts. Current flows up through the TL431, out of the anode and goes to ground through R6, the 1K resistor. This establishes the normal current flow for this device to operate properly. So by adding plus 2.5 volts to the negative 12 volts, we get a constant minus 9.5 volts relative to ground across R6. This voltage is connected to the base of NPN transistor Q2. Since the base is held at a constant minus 9.5 volts, by its nature the emitter will be 0.65 volts more negative, or 10.15 volts absolute. Subtracting 10.15 volts from the minus 12 volts gives us the voltage drop across R3, a 931 ohm 1% resistor. The equation shows that 1.85 volts divided by 931 ohms equals a current of 1.99 milliamps. This is 2 milliamps for all practical purposes. The exact current value is not overly critical, only that it does not change under load or over temperature. If you recall your bipolar transistor theory, the current in the collector circuit is approximately equal to the current in the emitter circuit. For this discussion, we assume these two currents are equal. The emitter current will contain the base current as well, but since the current gain of this transistor is significantly higher than 100 times, the base current can be ignored. This new constant collector current travels up towards the emitter resistors of the two transistors in the differential amplifier above. At the bottom of the two resistors R2 and R5, the current is split into two paths. Assuming that our transistors are perfectly balanced for the moment, the current will divide evenly and 1 milliamp goes through each transistor. Again, assuming the same current emerges from the collectors of Q1 and Q3, this will cause a voltage drop of 150 volts across the 150K resistors R1 and R4. Observe the top of these resistors are at a DC level of plus 300 volts. Therefore, 300 volts minus 150 volts results in plus 150 volts on the collector of each transistor. When perfectly balanced, the voltage difference between the collectors is 0 volts. Does this circuit seem strangely familiar? Remember the positioning pots in episode 1? The way that one pot's voltage would increase while its twin's voltage decreased by the same amount? This circuit does exactly the same thing, only with no moving parts. Since the current is constant as the signal-driven transistor Q1 turns on more, it takes more than its fair share of the current, while its partner Q3 now has less current available. The current going through R1 increases and the voltage at the collector of Q1 goes down, let's say by 10 volts. Conversely then, the current at the collector of Q3 must go up by the same amount, or 10 volts as well. The voltage difference between the two collectors is now 20 volts. The key purpose here is to generate two amplified high voltage signals that are mirror images of each other to drive the deflection plates in our CRT. These signals are AC coupled to the deflection plates, so the current configuration is not suitable for general purpose oscilloscope or for the SparkFun o'clock board after all. We will look into that in a future episode or a separate series on that topic. Not mentioned up to this point is the capacitor C2, labeled with the value TBD. This stands for to be determined. The function of this capacitor is critical in getting the best AC performance possible from this amplifier. This capacitor is wired in such a way as to increase the AC signal gain as the frequency increases. This will flatten the frequency response as well as equalize the overshoot and undershoot properties of the outbound signals. No need to dive into how this is accomplished, as this discussion is about making the circuit work empirically. I am going to show you how I accomplish this in the simplest way possible. I designed a circuit board for these amplifiers and had it manufactured for me at OSH Park, Osh Park. You can easily find this company online with a simple search. I prefer Osh because they are located in the USA, making the delivery time much faster than the overseas suppliers. For very small boards, Osh's prices are excellent. 3 of these cost me just under $23 US. Delivery was within 5 or 6 days. Though I have this board posted on the Osh website, don't have them made at this time. This is version 2.0. Wait for version 3 or later. As mentioned earlier, the video amp portion was not tested before I made the board. It failed to work as expected. My bad. Back to tuning the impulse response of the amplifiers. It's time to break out the capacitor substitution box and connect it to the circuit board where these capacitors are located. This is a very handy tool for the empirical designer. Hook this up and dial it in. I placed all of the surface mount resistors and capacitors on the bottom of the board during layout. This keeps the top of the board tidy and clean looking. The TBD capacitors are located here and here. We connect some short wires that poke out for the substitution box alligator clips to grab. The test consisted of connecting 2 oscilloscope probes to the differential amplifier outputs in parallel with the coupling capacitors to the CRT deflection plates. 2 probes are used to provide a balanced load on the outputs during the test. A single probe might work, but this was not tried at this time. This method makes balancing the amplifiers easier. In the first photo, the probes are connected to the X channel. In this second photo, the probes are connected to the Y channel. On the right side of the image, you can see the 2 alligator clips from the capacitor substitution box connected to the 2 yellow wires that bring the TBD capacitor pads out from under the PCB. A word about the coupling capacitors. I originally used some 0.001 microfarad ceramic capacitors, also known as 1 nanofarad or 1000 picofarad, rated for 3000 volts and reasonably small sized. These 0.001 microfarad capacitors could pass the 15,750 Hz horizontal scan sawtooth waveform with ease, but the 60 cycle scan ramp was severely distorted and rolled off. So I increased the capacitance values by 100 times to 0.1 microfarads or 100 nanofarads, whichever scale you prefer. Notice these are rated for 2000 volts. A 1000 volt capacitor would work here too. But I bought these in bulk as I may need more voltage capability in future projects. They are very big compared to the rest of the components in this project, hence they live on their own board. This makes construction simpler and more flexible. I set my WaveTech signal generator to output a 20 kHz square wave at about 2 volts peak to peak and fed that into the plus input of the amp. Placing the scope into AC coupling, 50 volts per division on both channels, I adjusted the signal input level to make the boboscope CRT trace scan out to the edges of the screen. I did this in both channels before tuning was complete. Output from the amplifiers were in the range of 100 volts peak to peak or plus and minus 50 volts, as you will see on the scope screen. We could see the output square wave was not very square. It was rounded off quite a bit. I adjusted the substitution box to various values until the overshoot and undershoot was at the lowest I could get it. Starting at 100 picofarads, the waveform was rounded off. Going up in capacitance, the waveform became more and more square. Passing the optimum capacitance, the waveform began to overshoot, as you can see in the following sequence of photos. This is what the waveform looks like with 1000 picofarads dialed in. Better, but still rounded off at the corners. This is what the waveform looks like with 2200 picofarads dialed in. This was the best the wave looks using the substitution box's coarse values. We will return to this. First, let's see what too much capacitance does to the waveforms. This is what the waveform looks like with 3300 picofarads dialed in. Notice that the flats of the waveform are starting to hook slightly at the edge of the transitions. This is what the waveform looks like with 4700 picofarads dialed in. See that the range switch on the top of the substitution box has been moved to the higher ranges on the right side knob. 0.0047 microfarads is exactly the same as 4700 picofarads or 4.7 nanofarads. The waveforms are now clearly overshooting in a big way. This is what the waveform looks like with 15,000 picofarads or 0.015 microfarads or 15 nanofarads dialed in. Notice that the flats of the waveform are starting to hook wildly at the edge of transitions. This was as far as I dialed it up, as it had proven the point quite well. Going back to the 2200 picofarad setting, this was the best waveform I could get with the substitution box. The 2200 picofarad setting was rolled off slightly, and the 3300 picofarad setting was overshooting slightly. Fortunately, my capacitor inventory has a value in between these. It is 2700 picofarads or 2.7 nanofarads. I installed this value on the board and got the square wave outputs nearly ideal, or as close to it as this very simple design can get. This is most satisfactory for our purposes of passing the TV scanning ramps with the least amount of distortion. The rising and falling edges are as steep as possible given the limited bandwidth of these amplifiers. There is no overshoot or undershoot. The final step in aligning the deflection board is to balance the outputs of the amplifiers. I have switched over from square waves to television scan ramps at this point in the process. First, we connect the scan amplifier outputs to the CRT scan coupling capacitors. Then apply a scan sawtooth drive signal running between 0 and 5 volts peak to the amplifier positive input and plus 5 volts DC to the complementary negative input. Notice that these amplifiers are DC coupled, so the incoming signals must be between 0 and 5 volts. If you are driving an AC coupled signal into either input, then leave the other input floating and simply center that level pot. Adjust your gain with the pot of the driven input. If your CRT scan is reversed from what your design requires, you may either swap the output signals or the input signals, whichever is most convenient in your case. Next, connect the 2x10 scope probes to the outputs of the channel you are aligning. Use 2 probes to keep the output loading in balance. Set your scope to 50 volts per division. Ground the inputs and place both traces on the bottom line of the graticule. We need to be able to see the signals sitting on approximately 150 volts of DC, which will be 3 divisions up from the bottom graticule line. Set both inputs to DC and the scan traces will appear. Chances are each output is sitting on a different DC level. Adjust the negative input pot for each channel, RV2 or RV4, to make both waveforms perfectly overlap each other vertically. This assures that both signals are sitting in the center, most linear portion of the amplifiers. That's it. The amps are calibrated. This concludes the deep dive into the operation and alignment of the XYZ amplifier board. In the next video, we will do a deep dive into the tiny TV board, which provides horizontal deflection, vertical deflection, and video drive to the boboscope board. Hopefully now you know more about differential amplifiers and high voltage deflection circuits than you did before the video started. So next time we will be looking at the boboscope in part 4, but rightly so, perhaps we should call it the Bobo Vision. So until next time, Labguy out.